Okay, problem number 2. I know that this is going to be a calculator problem because when I read through it, it tells me there's 2 points of inflection on the graph, and it says write down the x-coordinates of these points. How can I possibly write them down just by looking at the first derivative? I get points of inflection from the second derivative. And remember, points of inflection are where the graph changes from concave up to concave down. So clearly I can't tell just by looking at this where it's changing from concave up to concave down. I need to take the second derivative. So, and then I would need to set the second derivative equal to 0 to figure that out. So when it says write down those x-coordinates, I actually have to do some work here. So this is kind of weird that it says write down. I'm guessing that this problem was changed from its original formatting, and there was a different first part of it where you actually had to do some work. So what we're going to do is we need to get the second derivative in order to figure out where the points of inflection are. We get those from the second derivative. So I'm going to take the derivative. 3 times negative 24 is negative 72. Subtract 1 from my exponent. 2 times 9 is 18. Subtract 1 from my exponent, plus 3. All right, we get points of inflection when the second derivative is equal to 0. So I'm going to set this equal to 0. And I tried factorizing it, and I had no luck. So that's why I decided this must be a calculator problem. So then I grabbed my calculator. Here's my calculator. I'm going to put this in negative 72 x squared plus 18x plus 3. And I'm going to go ahead and graph that. And I want to find where it's equal to 0. So let's zoom 6 that. See if we can spread it out a little bit better. Yeah, that doesn't look much better, but that's okay. What I need to do is I need to just find the x-intercepts. So from the graphing display calculator, I'm going to get my 2 x-intercepts. So I'm going to do second, calculate. I want my zeros. I'm going to go left. Oops. I'm going to go left at the first one and then right. Hit enter, and it gives me the first one. So that would be negative 0.114. And then the other one with a 0 to the left of it, to the right of it. Enter, enter, enter. And I get 0.364. Those are my 2 x-coordinates of my x-intercepts of the second derivative, which gives me my points of inflection. Okay, so notice we don't have the original function, so I wouldn't be able to really put this in. I mean, I could integrate it, I suppose, to try and figure out the original function, but never mind. We don't need to do that right here. Okay, next, let g of x equal the second derivative. Okay, I got my second derivative. Explain why the graph of g has no points of inflection. Okay, so if g of x is equal to this, then points of inflection, we find those by doing the second derivative. So if I take my first derivative, I get 72 times 2 is, I get negative 144 x plus 18. Oh, actually, I could probably stop right here and say why there's not going to be, actually, I didn't even need to do that, I don't suppose. Why there's not going to be any points of inflection. If I take the second derivative, I could go ahead and do that. The second derivative would be negative 144. So when does the second derivative equal 0? Never. It never equals 0. So the second derivative never equals 0, therefore there's no points of inflection. Okay, that's one way I could explain it. Another way I could explain it is the fact that g of x is an upside-down parabola. It's a sad parabola. Okay, so this is g of x is a parabola. And it's concave down. And it never changes concavity. Therefore, there are no points of inflection. because we have points of inflection. Oh, I spelled it the American way. That's the English way. Sorry about that. Doesn't matter. You can spell it however you want. There are no points of inflection because it doesn't change concavity, because the g of x is a parabola. All right, that's it.